So now we're going to talk about the non-inverting amplifier. Right, so we have inverting, B, this is C. Let's draw it out. We're going to put, again, the negative terminal is going on top. And then we have an input here. Another resistor here. And here, I'll draw it like this. We have an input. Let's call this V in. And we're going to ground this. Let's call this R F F R G. Okay. This is the non-inverting amplifier. You've never seen this before. Right? And you're asked, what is, as you can imagine, V out in terms of V in. So V in is now the input, and you want to know what is the V out. Seems complicated until you remember there's only two rules for op-amp. So let's apply them. The first rule of op-amp says that no current flows into the input. So I would write here that this is 0, and here that this is 0. So these rules, I mean, again, they're not mathematical equations. They're just draw it. We are now halfway done. Great. Second rule, V plus is equal to V minus. Okay, let's just write it. V plus is equal to V minus. And at this point, we're done with the op-amp. Right? It doesn't matter anymore. It's still there, but from our circuits analysis perspective, you can just go ahead and ignore it, right? All right, I'm not going to erase it, right? But I'm going to pretend like it's not there. All right, well, now what? I don't know. Ohm's law logic. I appreciate this is a little less defined, right? But let's think it through. Well, I want to start here. V plus is equal to V minus. But in this case, I know what V plus is, right? This voltage here, right? How big is this voltage compared to the reference is exactly V in. I mean, I'm giving it V in. I could have drawn it differently, but I drew it like this. So V plus is equal to V minus is equal to V in, right? V in is at V plus, but it also shows up here. Right now, are these points actually connected? They're not. But if this is V in, that's V in. Right? That is the application of rule number 2. Now, rule number 1 says there's no current here. And that is important because if I were to draw a current here and call it I, and I were to draw a current here and I would call it I, well, let's call it IG and IF. You will realize that IG is in fact equal to IF because any current flowing here must flow here. These resistors are in series, so they have the same current. You can say, oh, this sounds really repetitive, right? Welcome to my 405. It's super repetitive. It is the same ideas again and again and again, because that's all we need. Yes, it sounds very similar, but as we now take it to the next step and go through the math, which is just Ohm's law, you'll see it comes out a little different, right? Just because of the way the math works out. And in this case, let's go through the same thing, and let's just say, let's do Ohm's law across the whole thing. So I'm going to say what's the best way to do things? We'll try it that way. I is equal to, if I were to do it across the whole thing, I would get 0 minus V out over R sub G plus R sub F. That is Ohm's law across the equivalent circuit, right? Just like we did before. And then let me do one more. I'm going to do IG, but IG is I, right? So we'll say G in parentheses, I guess we don't really need to count it that way, is equal to, well, now I'm going to get 0 minus V minus, but V minus is V plus, and V plus is V in, minus V in, over R sub G. Now, these currents here are actually equal to one another, right? And the zeros don't add up to much, right? And so we will get, I'll do it here, minus V0 over R sub G plus R sub F is equal to minus V in over R sub G. And in a final step, V out is equal to V in times R sub G plus R sub F over R sub G. And unless I made a mistake, that is the equation for a non-inverting amplifier. And what do? We just applied the two rules of op-amp, right? And then Ohm's law. And we got it. And what does this circuit mean? Well, if R sub G was equal to 1 ohm and R sub F was equal to 9 ohms, right? Then we would see that R sub G plus R sub F over R sub G is equal to 10. And I'm going to put an X on this. A 10X. This is 10X. So by selecting a 9 ohm here and a 1 ohm here, I've created a non-inverting amplifier with a 10X gain. So that in this case, if 3 volt would come in, right? If 3 volt would come in, I would get 30 volts out. You could say, which one do you like? I don't know, use whichever one you want. Turns out you can daisy chain these. I could actually have an inverting followed by another inverting. And we started to talk about that last time, how with op-amp circuits you can combine them without messing everything up. So we'll come back to that. There's a little hint of some coming. And that's it. There is no op-amp circuit, and we will address slightly more complicated op-amp circuits that does not bend the knee, okay, to these two rules. Once you apply these two rules, you don't have to worry about the op-amp anymore. Now there is some additional, it doesn't, as you see, you don't just apply the two rules and the answer emerges. You have to apply the two rules, all right, and then do a little bit of Ohm's law, all right? Yes? Yes.
For the positive and for the inverting, does it have to be grounded, or can you put a source there?
In this implementation here, the positive is in fact grounded. And you'll notice that the input arrives on the negative side of the amplifier. Well, in this case, we have an input that is arriving on the positive side of the amplifier, and there is a ground sitting on the negative side. So there is a specific implementation.
So one of them is grounded and the other is
I mean, this is showing you where the grounds or the reference voltages are. Does it have to be grounded? I mean, if you put a voltage here, like 1 volt, then this would then be 1 volt. And then you'd have to walk through all this analysis, right, with 1 volt sitting here. And I don't know what that would give you, but you could do it. I want to show you how robust this approach is. I want to erase this. You know, there's something that professors never tell you is that before we solve a problem, we often have solved it already. And so then the professor's kind of going through a derivation, and it's like 20 lines, and at the end the result comes out, and you're like, how did they didn't know it, right? They knew it ahead of time. So I knew in this case, I kind of set it up in an easy way, but I want to now set it up differently. I want to do this. I want to say that I want to draw this current going the other way. I'm going to put it this way. And I'm going to call this, again, I sub g, but notice that I've drawn it the other way. If I had done that and then just plowed through with Ohm's law, would I still have solved the circuit? Let's see. So again, I've gone through rule number 1 and rule number 2, and then what I did is I wrote these, I wanted to do Ohm's law at these 2 locations, right? It's different than what I did before. So therefore, I sub g is going to equal, and now we got to be careful, right? Because it's not 0 minus this point here, which is Vn, right? It's actually Vn minus 0. So I have to write Vn minus 0 over R sub g. And then I'm going to say, well, IF, that one yes?
Let's say for this, would it still be right if you wrote negative IG equals to 0 minus Vn?
Absolutely. So the question is, could I have written negative Ig equals 0 minus Vn? Yes, absolutely. There's different ways. As long as you keep your positive. The only way this analysis fails, honestly, is if you mess up a positive and negative. Let's plot through it this way. I sub f is equal to, so this we did before, and the way I've drawn it here is going to be this voltage, which is Vn, minus V out. So we'll say V in minus V out over R sub F. Okay. Now, at this point, you might be tempted to say, well, IG is equal to IF. And this is why you're asking me about writing negative Ig, because there's a little bit of a trick here. If this here is, 10 cabs per minute, this can't also be 10. This has to be negative 10, right? If this is 1 milliamp, this can't also be 1 milliamp. This has to be minus 1 milliamp, which you have sort of avoided in this course, trying to up to now talk about negative current, right? But here you see it has to be that way. So in fact, I would have to write that I sub g is equal to negative I sub f, right? And this is where those positive and negatives can trip you up, right? You have to get it right. Having done that, I can now say that V n over R sub g is equal to the negative of V in minus V out over R sub F. And if I were to solve this out, I would get V, I'm looking at where I previously wrote it, is equal to V in times R F plus R sub G, this is a G, over R sub G. How do I know that? Because it's the same circuit. And this is what will come out. Don't believe me? Go through it yourself. Now you'll notice that the first way I did it, the math just kind of popped out a little easier, which is why I set it up that way. But this is not that hard, and you can get here as well. So don't worry about if you didn't set these up correctly. Like in this case, I started with this version of doing an equivalent, but then I abandoned it and I didn't use it, right? Whereas in the original version here, I did do it. It doesn't matter. You get to the same spot. Sounds good? Final few thoughts on this. So again, the easier way, right? You know, I've stuck to Ohm's law. And if you think about it, I'm still sticking to it. These are rules. These are not I mean, it's kind of an equation, right? But I'm not giving you any other formulation here, right? These are just rules they need to be aware of. Now, there is one other rule that I've left out, and this is very important. It matters in practice. Okay. I didn't put in here that this chip must be powered. And if you remember, there was another rule. I don't want to give up on 1 and 2, so I'm just going to call it rule X, because I don't, even though we're adding stuff here, I just wanted to tell you that there were just 2 rules, right? But this rule X is that V out must be between VCC plus and VCC minus. It cannot exceed these. Those are the guardrails that it cannot exceed. Let's think about what this means in terms of the inverting amplifier. Okay. I want to draw for the inverting amplifier the output versus the input. So the input can take on different values. It can also be negative. And then we have an output. And let's give this, well, let's stick with this gain of negative 10x. All right, the same design. So the gain is minus 10x. Okay. If, and I'm going to say, ooh, it could be a little crowded, but I'm going to call this 1, 2, 3, 4. Right here, I'm going to put minus 1, minus 2. And here I'm going to say, on this axis in a different color, because I've made it really crowded, I'm going to call this 10 volts, 20 volts, 30 volts, minus 20. Right, and here I'm going to put minus 10 volts, minus 20 volts, minus 30 volts. All right, I managed to make a very simple picture, very complicated, but follow it through. If the input is 1 volt, right, what is the output? If the input is 1 volt and the gain is minus 10, so think of it this way. This is the input, and this is the gain. The gain multiplies the input. So the input is 1 volt. The gain is minus 10. The output is minus 10. So I'm going to put that here. And I'm going to say, by the way, that VCC plus is 20 volts and VCC minus is negative 20 volts. Okay, let's go to an input of 2. If the input is 2, what is the output? Negative 20. And, you know, it's pretty good to say that this is like a line because it's that's right. V out is equal to minus 10. I mean, it is a line. And it has a slope of minus 10. If the input was minus 1, right, then the output becomes 10. And if the input is minus 2, the output becomes minus 20. And so we get this, right? This line here is the input-output relationship. Now, what if the input was 3? You might say, well, 3 times minus 10 is minus 30, but we hit this wall, right? We hit this wall, which I don't know, I'll keep it in black. And so in fact, at 3, the output is also minus 20, and the same thing is true for 4. And on this other end, we will also pin here. This line here corresponds to VCC minus, and this line here corresponds to VCC plus. And you can see why this is an important note. Because if you were to build this circuit and put in 4 volts and expect to see minus 40, you would not. And so this is not just an addendum, right? It is absolutely essential. When you are building op-amp circuits, your output cannot break across these guardrails. Conventional op-amp circuits, you're not going to be able to break across these guardrails that have been set up for you, right? And so, and you can say, well, that didn't come up here. No, it didn't, right? I mean, it doesn't show up at this equation or that one. It's just a rule number X. If we were to draw the input-output for a non-inverting amplifier, I'll do it right here. So this is for an inverting. If I were to draw the input-output for a non-inverting, and I will make this less messy, I would once again have, I called the same thing, V out. I would have a V in. And the relationship, which I'll draw in purple, will look like this, and then this. And these saturation points here correspond to VCC plus and VCC minus. And this here, the slope, is in fact the gain. Now, I didn't draw this as neatly as I would have liked, right? But if you can understand what I've drawn here, it means that you've been following all along. This gain is going to be set by this quantity, whatever resistors we happen to pick. You'll notice that this line is going upward because the gain is now positive, whereas this line went downward because the gain was negative, but we will hit these guardrails. So you can say, oh, I want a gain of 1 billion. I don't think that's going to work out very well for you unless your input is super tiny, right? So often we're working with gains of 100, 10, a very small signal, maybe 1,000, right? But not gains of billions because we're just going to immediately blow out into this range. right? And that is amplifiers in the amplification sense, right? I often in this course start with like a problem that we need to solve, and then I sort of show you how to use the tool. In this case, I did give you the tool before giving you, a problem, but anyways, I tried to make it as simple as possible. Any questions on this? All right. There will be additional amplifier circuits I will introduce. There's something called the difference amplifier. And then at one point, we're even going to be doing something very fancy as far as putting like capacitors here. Always got to go back to this. Always got to go back to this. This is not just a rule I'm giving you. That's how I think about it. Sounds good?